And neither of those have to go into your grade if you don't want them to, because the final can replace one of your first 4 exams if it's better than one of your first 4, and 1 quiz is dropped. So if they're good, that's great. It can count for your score. But if it's bad, just think of it as like some information about what my tests and quizzes are like, and use it in the future. Anybody have any questions about the quiz?
On the last question, what type of quantities?
Properties, any kind of property. Yep. Yeah. A material characteristic at a single state. So it just has to do with all the individual things that make up a state. And then a process is what takes you from one state to another state. Any other questions about the quiz? Okay. Next week, first we have exam 2, and that's on Tuesday. What's that? Tuesday the 2nd. And the topics for that will be everything up through linear interpolation. Okay, so you've already been assigned all the problems that are relevant for this test. Remember that it's cumulative, so you need to make sure that refresh your memory on the older stuff too. But and I guess at the start of today, I'm going to say one thing that if you've worked on all the interpolation problems yet, one thing that will help you with those. Any questions about the test? No, I'm just going to do it. I just sort of think of it as like statistical sampling. So I'll just pick something here and there. It'll always be a little heavier, slanted towards the newer stuff, but I'm always going to just take a topic or two from the old stuff and put it in there. So you just, need to try to be ready for whatever old stuff is on there.
What we've learned mixed into one question.
No, all the questions are going to be similar to questions on the homework, but there could be, if there's 4 questions on the test, there could be 2 that are on new material and 2 that are on old material or something. Any other questions about the test? Okay, and then the second thing next week is I'm picking up the binders for the first time. That'll be on the 4th. And so that's going to be 5% of your grade. just making sure that's complete. You should have class notes for every class meeting. You can go back and check what I said about binders the day we talked about the syllabus or whatever, but if you missed the class, you can just print out notes from the PDFs on D2L, but there just needs to be complete notes for every class. And then I'm going to be checking for completeness and care for your work for the homework assignments. And you need to have, so there have been a lot of problems assigned twice, and so those need to be in there twice. And I don't care how you organize it. If it makes more sense to you to put all the 2 times you do number 1 on first law together, that's fine with me. If you want to put all the second time through in a separate section or something, that's fine with me. Whatever makes sense to you. It just needs to be in there, because I think revisiting that stuff is an important part of just solidifying it in your head. And then, so you're giving them to me on Thursday. I'll get them back to you on the next Tuesday. That'll be my main priority. So, because it's sort of a pain to go through a long time without those binders. Anybody have any questions about turning in the binders? Okay, so that's next week. So first, are there any homework questions? If there are any homework questions, I'm guessing it's related to the first thing I need to talk about today. There are a couple of questions that needed, where you needed to deal with quality. Yeah, any homework questions? Let me know. Okay, yeah, right. Yeah, I know it's hard to keep all that. Well, I'll have to think a little bit about assignments after class and whatever, but if I do give you a new assignment for Tuesday, it'll be something short, and then I won't give one for Tuesday, so you'll have some time to get stuff together for the binders. Yeah. Okay. So that's the one where it lists temperature, specific volumes for a material. It doesn't, it's the same process no matter what it is. It's at 2 different pressures. So you're given a table for ammonia. At a pressure of 1 megapascal and 1.5 megapascals. And we want to estimate for part A the specific volume at 240 degrees Celsius and 1.25 megapascals. Okay, well, the table has these 2 pressures, and it has the temperature 240 degrees. So 240 degrees Celsius is included. So we want to estimate the specific volume. At a pressure of 1 megapascal and a temperature of 240 degrees Celsius. The specific volume that's given is 0.2275 cubic meters per kilogram. That's just reading off the table. And at a pressure of 1.5 and a temperature of 240 degrees Celsius, specific volume is 0.1483 cubic meters per kilogram. That's read off the table. And we want to use that to approximate the specific volume at 1.25 megapascals. So we can think of this as like we have a function of, since everything's at 240 degrees Celsius here, we can just think of this as a function of pressure. And that's equal to the function value at pressure 1 plus the function value at pressure 2 minus the function value at pressure 1 divided by pressure 2 minus pressure 1 times delta P. Okay, so the specific volume at 1.25 megapascals, this isn't exact, this is the idea, this is an approximation. So this approximation is, that's going to be the specific volume at, we'll call this pressure 1 and this pressure 2. Here's an interesting thing. It would come out the same no matter whether we used this as pressure 1 and this is pressure 2 like I have written, or if we switch those. Either way, it's just calculating a line between those two and finding the spot on the line. So it doesn't have to be pressure 1 is the smaller one and pressure 2 is the bigger one. But it does have to be that your two independent variables have to bracket the value of the independent variable you want. So this wouldn't work if we knew this at a pressure of 1.0 megapascals and then also knew it at a pressure of 1.1 megapascals. Okay, that's not interpolation, that's extrapolation, and that is, you can usually expect that to be inaccurate. So it has to bracket. Okay, so what's the specific volume at 1 megapascal? That's 0.2275. And now plus the pressure, the specific volume at pressure 2, so that's 0.1483 minus 0.2275 divided by 1.5 minus 1. And then our delta P is 1.25 minus 1, so that's positive 0.25. And someone want to calculate that? 0.1879 meters cubed per kilogram. And then if you had the mass of the material that you have, you could multiply by that and get the total volume. Let's do part C. So part C, what's the specific volume at 220 degrees Celsius and 1.4 megapascals? Okay, so this one, we're going to have to interpolate on the temperature and interpolate on the pressure. 220 isn't in our table, and 1.4 isn't in our table. So so now specific volume is a function of two independent variables. You can think of this as V is a function of temperature and pressure. Doesn't matter which one you think of as the first variable. So I'm going to give the four values that we have. I'm going to do it in this order. Temperature is going to be my kind of like my X variable. Pressure is going to be my Y variable. So my specific volume at the lower temperature that we know, and at the higher pressure, I'm just doing this the way the grid would kind of look in an XY plane. So the higher pressure is 1.5 megapascals. And that is 0.1325. Specific volume at the higher temperature, that's 240. And the higher pressure, 1.5, is 0.1483. And then the specific volume at the lower temperature is, so that's a temperature 200, and the lower pressure is 1. So that's 0.2060. And the specific volume, temperature of 240, and the pressure of 1 megapascal is 0.2275. So that's just read right out of the table. And so now we're going to do this in 3 steps. So I'm going to first calculate the specific volume at 220 degrees Celsius and a pressure of 1 megapascal. So to do that, I'm going to, it's going to be 0.2060 plus 0.2275 minus 0.2060 divided by 240 minus 200 times delta temperature, which is 20. Can someone multiply that out, calculate that for me? 0.21675. And then I'm going to calculate the specific volume at 220 and a pressure of 1.5 megapascals. That's 0.1325 plus 0.1483 minus 0.1325 divided by 240 minus 200 times 20. And what do you get for that? 0.1404. And so now we have approximate values for the specific volume at two different pressures, but the same temperature. And so now the third one is just going to use our two estimates here to calculate the value at 1.4 megapascals. So now the specific volume at 220 and a pressure of 1.4 megapascals is equal to 0.21675 plus 0.1404 minus 0.21675 divided by 1.5 minus 1 times 0.4. And what do you get for that? .155. Okay. And that's meters cubed per kilogram. What would be the problem if I would have, okay, so we always have these three steps, okay? What if instead of my first step being to calculate the specific volume at 220 degrees at the two pressures, what if my first step had been to calculate the specific volume at 1.4 at the two different temperatures? And then we use those to calculate this. Would there be a problem with that? That's perfectly fine. It doesn't matter which one of these we do first. Would we get the same exact answer? No, but it would be, as good as the other one, as far as we know. So the order of variables or whatever, that doesn't matter at all. But you first use basically one of the variables to get that variable to the value you want, and then you use linear interpolation on the other variable to approximate it. Any questions about either of those? Any other homework questions? Yeah. Number 2. Okay, so gas is contained in a closed tank. An electric resistor in the tank transfers energy to the gas. So energy goes to the gas. At a constant rate of 1 kilowatt. And there's heat transfer from the gas to the surroundings. This is electrical energy. And there's heat transfer from the gas to the surroundings. So energy leaves the gas at a rate of 5t watts. Where t is in minutes. And this is heat energy. When you're talking about electric energy, that's considered work. What's the change in energy of the gas as a function of time? And then we want to plot it versus time. Okay, so let's first set this up with the differential first law. So we know that the E dt is equal to Q dot minus W dot. Our W, we have the gas doing work on the surroundings. Nope, I have that backwards. We have electrical energy coming into the system, so the surroundings are doing work on the gas. So is W positive or negative? So W dot is equal to -1 if we do all this in kilowatts. And then Q dot, we have energy leaving the gas, so is that positive or negative? That's negative also, so that's -5t. With t in minutes. So the EDT is equal to -5t minus -1. So it's equal to 1 minus 5t, where t is in minutes. And that value is in kilowatts. So you can think of this as the EDT is equal to 1 minus 5t kilojoules per second with time in seconds, with time in minutes. I bet I just wrote that down. Oh, you're right. That's funny. Okay. So this one is just watts. Okay, so let's change this constant to 1 times 10 to the third. Okay, and this is in minutes. If we want to get, and so now this is in joules per second. If we want to integrate this with respect to time and get joules out, we need to convert this time to seconds. So I'll rewrite this as the EDT is equal to 1 times 10 to the third minus, divide this by 60 to get time in seconds. And you get P over 12. That's something like 0.083 repeating. Is that right? 1/12 P. And this is in joules per second, time in seconds. And now we can just integrate this. So you can think of, if you use separation of variables, dE is equal to 1 times 10 to the third minus 0.083 repeating t dt. And you can integrate both sides. You can think of this as an integral from 0 to t. And if you want to be careful about it, you'd make this a dummy variable. Okay, so E as a function of time is equal to 1000 t minus 0.0416 repeating times t squared. And so if you have internal energy, well, not internal energy, total energy of the gas on the y-axis and time on the horizontal axis, you have something that starts out at 0. I got rid of the constant because we'll just arbitrarily say at time equals 0, there's no energy in there. And it's going to start out steep and trail off. This is a parabola. Any questions about that? Any other homework questions? Yes. The value at the top of the parabola, well, if you, I guess you could take the first derivative, set it equal to 0, and yeah, maximize it. Does it ask for that specifically? Okay, curious. Yeah, so just maximize that function. Okay. So now, one thing I want to say that I think comes up in the last 2 problems on the linear interpolation homework is using quality. Remember, I defined this quality X we'll use it for specific volume, specific internal energy, and specific enthalpy, which we're going to talk about very soon. For materials, at saturation temperature and pressure. Okay, so quality, remember, is equal to the mass of the material that's in the vapor state divided by the total mass of the material. So that's the mass of the liquid plus the mass of the vapor. The idea of quality only makes sense if you're at saturation. Otherwise, the material's all vapor or all liquid. And if the material is all vapor, the quality is 1. If the material is all liquid, the quality is 0. So let lowercase q be one of the properties lowercase v, lowercase u, lowercase h. Then the total value, the overall value of that property is equal to 1 minus the quality times the property value for liquid, which you can look up in the table, plus the quality times that property for the vapor. So we have the total specific volume is equal to 1 minus x times the specific volume for the liquid at that saturation point, plus x times the specific volume for the vapor at that saturation point. I'm just going to write all 3 of these out. For specific internal energy, U total is equal to the quantity 1 minus x times U for the liquid plus x times U for the vapor. And for enthalpy, which we haven't defined yet, the total is equal to the quantity 1 minus x times H for the liquid plus x times H for the vapor. Basically, you're just sort of doing a weighted sum of those 2 parts. So if your material is 20% vapor and your quality is 0.2, and so you have 0.2 times the specific volume for the vapor plus 0.8 times the specific volume for the liquid. You add those 2 up and it gives you the total specific volume. So let me do an example. So let's say that we have water that's at saturation. So it's either saturated liquid or saturated vapor or some combination of the 2. Pressure of 5 bar with a specific volume of 0.15 cubic meters per kilogram. So first, what's the temperature? And second, well, Second, what's the quality? X. And third, what's the specific energy? Okay, so it's water. It's saturated at 5 bar. So saturated water. Ooh, that's the thing I was looking for the other day. So let's go to the water table. So saturated water, and we want to do it indexed by pressure because we know the pressure. So I'll go to this one. We're looking for the temperature at 5 bar. So that's right here. Can you see my cursor? So the temperature, since we know it's at saturation, is 151.9 degrees Celsius. And now we need to calculate the quality. We know that the total specific volume is 0.15 cubic meters per kilogram. So we can use that. 0.15 is equal to 1 minus the quality times the specific the specific volume for the liquid. And so for saturated liquid at 5 bar, that's 1.0926 times 10 to the minus third, because if you look up here, this is 1,000 times the value. So 1.0926 times 10 to the negative third. Plus X times a specific volume for the vapor. Go to 5, go over here for a saturated vapor. It's 0.3749. And if you calculate, oh, I haven't done it. Okay, so 0.15 is equal to 1.0926 times 10 to the minus third. Plus 0.3749, quantity 0.3749 minus 1.0926 times 10 to the minus third X. So can someone calculate X? Okay, 0.3983. Okay, so 39.83% vapor by mass, and then the other 60% is liquid. And then the last question is, what's the specific internal energy? So we know that the total specific internal energy is equal to, what's that, 0.6017, 1 minus 0.3983. times the specific internal energy for the liquid. So we can look that up in the table. So that's here in this column. So 639.68. You see that? $639.68, and then plus 0.3983 times the specific internal energy for the vapor. So that's in the saturated vapor column for internal energy, 2561.2. And can someone calculate that? 1,000, say it again. 0.02, and what were the units here? Kilojoules per kilogram. And then if you're doing something like this, where you're using the first law of thermodynamics, this is at a single state, right? That's a property. You can multiply it by the mass and get the capital U, the total internal energy at that state. Then look at the other end of the process you're dealing with. You'll calculate some different internal energy, subtract those to get delta U, the change in internal energy, and then that goes into your first law of thermodynamics. Any questions about any of that?
Are we going to be needing to reference the table?
Let me look. Yes. And all the tables are on D2L. And if you need a table on the test, so yeah, you should make yourself a little familiar with the layout of the table, just how you would look things up in the table. I'll provide any table that you need on the test. But the things you need to, there's not too much to it. You just have to know that if you're dealing with saturation, you can do it by temperature or pressure, you choose. And you just go down one list to the temperature, the pressure that you're dealing with. And if it's a compressed liquid or a superheated vapor, then you have to go in chunks by pressure, find the pressure you want, and then inside that pressure, go through the list of temperatures. And you might have to interpolate in those cases. If you're dealing with saturation temperature and pressure, the interpolation is only going to have one independent variable. In general, when you're dealing with a liquid or a vapor, it's going to have two independent variables, and you're going to have to do that three-step process. So let's talk about, there's two quantities, well, three, I guess, two types of quantities that I want to talk about. So say three new quantities. And those are enthalpy, that's capital H, and in the tables, there's specific enthalpy, which is lowercase h. And then there is lowercase c sub v and lowercase c sub p. And these are the specific heats. this is enthalpy. Okay, so first, enthalpy. This value of capital H is equal to the total internal energy plus the pressure times the volume. There is kind of a rough physical interpretation of this. You can roughly think of this as the internal energy plus the energy required to move aside the surroundings to put the material in place. Okay, so like let's say that our system is this much air in the middle of the room, okay? So what we're talking about is the amount of internal energy that's in this amount of air plus the amount of energy it would take if you had that amount of air separate and all the rest of the air was in place and you had to go in there and fight the atmospheric pressure to make space to put this extra air in. Okay. Thinking about it physically, I don't find it really necessary for anything that much. Maybe the question is, what's the point of enthalpy? Like you could make up all sorts of crazy variables by adding this and multiplying this. Enthalpy arises as cross terms in deriving the first law of thermodynamics for a control volume. Okay, so we haven't dealt with control volumes yet. We've only dealt with fixed systems, material that like where through the whole process we're tracking the same amount of material. But we'll also deal with cases where, like for example, you're pumping water, water's coming through a pump, and so that material, as the process goes on, starts outside of the material, outside of the volume you're looking at, then pumps into the volume you're looking at, then pumps out, and you have to deal with that. And we'll see when we go through that derivation that you come up with these terms equal to enthalpy. So really, you can just think of this as it's stuff that's helpful in calculations. It turns out that a lot of times, if your table gives you this value, it makes your job easier. Okay. So if you don't want to think about its physical meaning, I don't think you lose anything really. H is an extensive property. So it's a property and it's extensive. So remember both of those. And it has units of energy. And the tables give the specific enthalpy, lowercase h, and that has units of energy per mass. So for example, joules per kilogram. One thing to notice, so I'm going to do one example, is all of the things that make up the enthalpy. Oh, and this lowercase h equal to the specific internal energy plus the pressure times the specific volume. Makes sense because the extensive internal energy is just the mass times specific U, and the extensive volume is just the mass times the specific volume. So if you multiply lowercase h by m to get uppercase H, you get it's the same thing as uppercase U and uppercase V. But what I was going to say is, so since you can calculate it like this, and all three of those things are properties that are also in the table, there's really no need to have a separate column for enthalpy. It just comes up so often that it's easier to just read the value of enthalpy off the table than to calculate it like this each time. You know what I mean? Okay, so let's say we have 2 kilograms. So 2 kilograms of liquid water. And let's say it's saturated at 1 bar of pressure. Calculate the enthalpy, the extensive version of enthalpy, from table values of U, P, and V. Okay, so we want to deal with the saturated water table, and we want it indexed by pressure because that's the independent variable we're given. And I still have that one open. So 1 bar of pressure, that's right here on the table. And now we can just go across and read off these different values. We're talking about liquid water. So the specific volume is 1.0432. This is for the fluid. Yeah, I hope so. Okay, 1.0432 cubic meters per kilogram. And then we have to calculate pressure. Oh, well, we're given the pressure. That's 1 bar. And we're going to do this. You can't do this calculation if your units don't match. So our pressure is 1 bar, and that's equal to 1 times 10 to the 5th pascals. And then the last thing we need is the specific internal energy. And so at 1 bar, specific internal energy, we want the one for the saturated liquid. So that's 417.36, and that's in kilojoules per kilogram. So this is 417 point, what did I say, 46? 417.36. And if we want it in joules per kilogram, we have to multiply this by 1,000. And then I think I left off something up here. Let me go back and look at the specific volume for the liquid water. So for a saturated liquid, we have 1.0432, but that's times 10 to the minus third. And that's in cubic meters per kilogram. Now all these are in SI units. So the enthalpy for the saturated liquid is equal to the internal energy, 417.36 times 10 to the third, plus the pressure times the volume, so that's 1 times 10 to the fifth, times 1.0432 times 10 to the minus third. And that comes out as, so let's see, we got 417.36 times 10 to the third, plus this is going to give us 104.32 times 10 to the third. Seems right. And so you get 521.68. And what are the units? That should be in joules, because everything's in SI units. We want the total value, the extensive enthalpy. So that's equal to the mass of the material, 2 kilograms. Oh, joules, this is joules per kilogram because it's intensive. And so this is equal to 2 kilograms times 521.68 joules per kilogram. And so that's 1,042. Okay, 0.36. Yes. To the second, 1.0432 times 10 to the second. This is oh, no, times 10 to the third. Oh, okay. Thank you. So Okay, so okay, so 417. Okay, 4, 6, 4, 3, 2 times 10 to the third. That's, I don't know why. I just have the extra times 10 to the third on there. Okay, so that's joules per kilogram, or if you leave this off, it's kilojoules per kilogram. I think so.
If you do it with the point there, then it would be heated.
So this is in joules per kilogram, and then yeah. Okay, so now this is in kilojoules. This is in kilojoules, and the answer is going to be in kilojoules. And the answer is 834.92. Okay, so now, hopefully, if we got the right answer, when we look in the table under the specific enthalpy for liquid saturated water, it should be this. Otherwise, we're doing this whole problem over again. Not really. Okay, so pressure 1 bar, go across the enthalpy, saturated liquid, 417.46. Yes! And it's in kilojoules per kilogram. Oh, yeah. Whew. Any questions about that? All right. And then the other two things, new things that we have to define. So first we defined enthalpy. Now we're going to define these two specific heats. So remember that U, in general, for a simple compressible substance, is a function of two properties, right? This is a property. To find the other properties, you need to define two of them. I'll think of it as a function of temperature and volume, specific volume. And enthalpy we'll think of as a function of temperature and pressure. Okay, you could choose any two properties, but these are the ones we're choosing. And so the specific heat with constant volume is defined as the partial derivative of the specific internal energy with respect to temperature, holding the specific volume constant, and the specific heat with constant pressure is the partial derivative of the specific enthalpy with respect to temperature, holding the pressure constant. So what that says is that this is a value that changes as CV changes as the specific volume changes. CP changes as the pressure changes. And we're going to use this relationship. So that relationship is complicated. Okay? I'm going to ask about this definition on a quiz, though, so at least one quiz. So just remember that relationship, because what's going to happen is, like, for example, under certain conditions, we're going to see that the internal energy loses most of its dependence on volume. And so often we can approximate the specific internal energy as a function of temperature alone. Okay? And if you can approximate U as just a function of temperature, that's not always true, but in some cases it's going to be true, then this complicated thing becomes simpler. It's just the derivative du dt. It's not a partial derivative. You don't have to worry about v anymore. Okay. And if CV is du dt, you can do integrations with this to figure out the change in internal energy just based on the temperature. Okay. So we're going to use stuff like that. The definition is complicated, but when this is going to be useful to us is when they simplify. Okay. And the way that, like, I think some of you talked about specific heats in physics 1 probably. And the way you would have talked about it is, like, for example, for liquid water, you know that it takes about an increase in energy of 1 kilocalorie. Is it 1 kilo? Maybe it's 1 little calorie to raise the temperature of a cubic centimeter of water by a temperature of 1 degree. Okay, so that's the specific heat, and that makes it seem really simple, right? That's because when water is a liquid, we have one of these simplified cases. But the simplified cases are going to come from this definition, so I want you to remember that. Okay, so next class is the test, and then the class after that, we'll get back into this and use some of these things. Any questions? The quiz? I think there's not a quiz. When is the quiz? Okay, so next Thursday, I missed that. I just looked at the schedule today. So next Thursday, there's a quiz and you're turning in your notebooks? I might have just skipped ones for the, I can look. No, I'll put it on D2L. But yeah, if there's a quiz, it will be up through today. Oh, okay, great. Yeah. So I just canceled it, I guess, because of the binder check.